Okay, so welcome to today's revision session. Okay, we are revising chemistry test 2, which is just simply biochemistry. Okay, so this paper has 3 sections. This section A, which contains 50 multiple choice questions. Okay, and then there are structured questions in section B and C. So we're going to answer all of the questions in this paper. Okay, so let's start from section A. Okay, so these are the questions in section A. We start from there. Okay, we start from there. So section A questions, they are just multiple choice questions. Okay, so section A, question 1, okay, they're saying identify the amino acids containing non-polar aliphatic arar groups. Okay, so non-polar aliphatic arar groups simply means the amino acids that contain side chains made only of carbon and hydrogen. Okay, and they do not dissolve well in water because of the word aliphatic there. Okay, so we know that of the 20 amino acids, okay, they are divided into groups. Okay, so we have the non-polar ones, we have the polar ones, and then we have those that are positively charged, and then we have those that are negatively charged. Okay, so those are the 4 types of classification that you have to know, okay, based um, on what they are. Okay, yeah, so we have the ones that are non-polar, we have the ones that are polar, we have the ones that are positively charged, and as well as the ones that are what? Negatively charged. Okay, so the option that have been given there, they are grouped based on those 4 groups that I've said. Okay, so when you consider phenylalanine, tyrosine, and tryptophan, okay, so these amino acids here are aromatic. Okay, they are aromatic and they contain benzene side chains. Okay, they contain rings, so they can't be the answer here. Okay, they are non-polar. Some of them are non-polar, yes. Okay, but they contain a side chain that has a benzene ring. Okay, so if it contains the side chain data, that is it contains the side chain that is a benzene ring. Okay, then it means it's not aliphatic, because we said non-polar aliphatic simply means those non-polar amino acids, okay, that contain side chains that only have hydrogen and carbon. Okay, so option A there wouldn't be the best answer. Okay, it's not the answer. And then B, they're saying glycine, alanine, and leucine. Yes, this here is the answer. Why? Because glycine has a side chain that has only hydrogen. Okay, alanine has a side chain that only has carbon and hydrogen, as well as leucine. Okay, and then this lysine, arginine, and histidine. Okay, these here are positively charged. Okay, they're positively charged. Okay, and then serine, cysteine, and the amino acid that I've listed on D there. Okay, those ones are polar. Okay, those ones are polar in nature. So the only answer there is B. So we pick B. So this tells you that you actually have to know the 20 amino acids. So I've put them here, okay, for your easy understanding. Okay, so you have to understand clearly, okay, and master these amino acids. So the ones I've put in orange there, they are non-polar. Okay, the ones I've put in yellow, they are polar. And then the ones in green, they are negatively charged. And then the ones in blue, they are positively charged. Okay, so there we had said the answer was um, this one here that contains glycine, alanine, and leucine. So we are saying these are non-polar and their side chains are what? Aliphatic. So let's confirm. So if you go on glycine here, you see that the side chain is just hydrogen there. Okay, alanine, the side chain is just contains hydrogen and carbon. Okay, so that means it's aliphatic. Okay, and then the other one, the amino acid, the other one was leucine. So leucine is here. So you see that its side chain, okay, only has carbon and hydrogens. So that makes it aliphatic. Okay, and then there are also other, okay, amino acids that have a side chain that is aliphatic. So for example, valine, you can see it, the side chain only has carbon and hydrogen. Even this guy here, okay? The side chain order is carbon and hydrogen. It's isoleucine, okay? And then now, when you talk about methionine, tryptophan, okay, phenylalanine, and then protein, these contain side chains that are not what? Aliphatic. Okay, why? Because, for example, if you go on tryptophan here, okay, you can see a benzene ring somewhere there. Okay, check phenylalanine, benzene ring. Okay, so these ones here cannot be aliphatic. And then what other options they are there? They were saying cysteine, serine, threonine, this one here. Okay, so this one here, this guy here, okay, it's polar as well. So when I go here and I go on the polar amino acid, this one's in yellow. You can see this serine is there. Okay, this guy is there and cysteine is there. Okay, so you have to master this table, guys. Okay, the way I've grouped them here. Those that are non-polar, those that are polar, those that are negatively charged, and those that are positively charged. Okay, so the easiest of all these to master are these ones here that are negatively charged. Okay, then the ones that are negatively charged, it's aspartate and glutamate. Okay, or you can say aspartic acid and glutamic what? Acid. Those are negatively charged. There are just two of them. So master them. So next time the question can come like which of the amino acids that have been given here are polar. Okay, so you have to know that it's serine, it's cysteine, this guy, tyrosine, okay, and all these that are in here or here. So you can mention any of those. Okay, so the best answer there, we're just saying it's what? It's what's happening now to my eraser? The best answer there, we're saying that it's B. Okay, because B has alanine, it has leucine, and then it has glycine. So those are non-polar and they contain aliphatic aryl groups. Okay, and then number 2 here, they're saying the 2 amino acids having aryl groups with a negative net charge at pH 7 are, okay, from mentioning these, the ones that are negatively charged, there are just 2 of them. It's aspartate and glutamate. Okay, so we're going to choose option A here. Okay, so you can take a screenshot of this table here so that you easily identify the ones that are polar, non-polar, negative, and positively charged. Okay. So there we're going to go with option A. Okay, let's go to part 3. Part 3, they're saying if the pKa1 value is 2.34, okay, the pK2 value is 9.60, then the isoelectric point Pi is equals to, okay, so the isoelectric point is not hard to find if you have 2 pKa values, okay, so just add the pKa values and then you divide by 2. Okay, so when I do this, my calculator is giving me 5.97. Okay, so is there a 5.97 on my options? Yes, so I pick B as my answer. Okay, but what is isoelectric point? Okay, so isoelectric point is just the point where the amino acid has 0 overall charge. Okay, it has 0 overall charge. That's the isoelectric point. All right, so that's the answer there. That's what we're going to pick. Okay. And then we move to part 4. So part 4, they're saying during the formation of a peptide bond, which of the following takes place? Okay, so before we even read these options, let's draw it. So a peptide bond is formed between 2 amino acids, right? Okay. So we know that the peptide bond will be between, okay, the carboxyl group of one amino acids, okay, and the amino group of the other. Okay, so the carboxyl group, it is something like this. And then here you have DH bonded to whatever it's bonded. And then this guy, the amino group, okay, it will have H and then N and then N. And then look, it's bonded to whatever it's bonded. Okay, so for the peptide bond to form, okay, the hydroxyl group of this carbonyl, of this carboxyl group, okay? The hydroxyl group is this one, the OH, okay? And then together, this is the carboxyl group. So the hydroxyl group of the carboxyl group, okay, bonds with one of these hydrogens of the amino group. So this hydrogen here and this hydrogen will bond and they'll form a water. Okay, so meaning that what we have now will just be C double bonded to this, and then this bond here, the OH has gone, the H has gone. So here I just remain with N, bonded to N. Okay, and then here bonded to whatever amino acid, even this one bonded to whatever amino acid. So this one here that I've written is what we call as the peptide bond. So it happens, okay, between the hydroxyl group, okay, from the carboxyl group and the hydrogen atom from the amino group. Okay, so now when you come to your options, you just look for something that will mean whatever I've explained here. So there, when you go on option A, they're saying the hydroxyl group, okay, is lost from its carboxyl group. This is correct, of one amino acid, and a hydrogen atom is lost from its amino group of another amino acid. Okay, so this is the statement that is true here. All these here are false. Okay, all those others there are false. So you choose option A as the best answer. Okay, so let's erase this and then continue. Okay, so here they're saying shown below is the structure of a certain antiviral drug. It is a nucleoside, okay? It is a nucleoside analog. Use the given structure to answer questions 5 to 9. Okay, so this is the diagram that we've been given there. So the first question they're saying, what nitrogenous base is in this drug? Okay, so we know that nitrogenous base, they are divided into two major groups, okay? We have the purines, okay? So the purines, we have the guanine and then the adenine, okay? And then we also have the pyrimidines, okay? So the pyrimidines, we have the uracil, the thiamine, and the cytosine, okay? So the major difference between the purines and the pyrimidines, in case it comes, is that these purines, okay, have two rings in their structure. And then the pyrimidines only have one ring. Okay, so now the pyrimidines are three. Okay, we have the uracil, we have the thiamine, and then we have the cytosine, right? Okay, so how can you identify their structure easily? Okay, how can you identify their structure easily? So I'll start with thiamine. Okay, so the thiamine has an extra methyl group on its structure. Okay, it has an extra methyl group. So it has CH3 somewhere on its structure. Then when you just see that, just know that, okay, this pyrimidine here is thiamine. Okay, and then when you talk about cytosine, okay, when you talk about cytosine, cytosine has one carbonyl group and an amino group. So on its structure somewhere, you expect to find the amino group, this guy, and a carbonyl group, which means just an oxygen double bonded to the ring. Okay, you're supposed to see these two. Okay, and then for the uracil, okay, for the uracil, you are only supposed to see you are only supposed to see two carbonyl groups. So meaning in its ring, you have an oxygen double bonded somewhere and then another oxygen double bonded somewhere. So if you see two carbonyl groups there, that is uracil. If you see a methyl group, that is thiamine. If you see an amino group, okay, and a carbonyl group, then that is cytosine. So when I look at this nitrogenous base that is connected here, what can I see? Okay, I can see a carbonyl group, this one, and I can see an amino group. So meaning that this nitrogenous base there is cytosine. Okay, the nitrogenous base there is actually cytosine. Okay, so I've also put the diagrams here, okay, in case you want to see them. So you can see I put the purines first of all. So we have guanine and adenine there. Okay, so and then the pyrimidines, we have three of them. Okay, if there is cytosine, you can see on cytosine, I have a carbonyl group and an amino group. Okay, on thiamine, I have a carbonyl group there and a carbonyl group there. So I have two carbonyl groups. So that's what you can use to easily identify um, the thiamine there. Okay, and then for, oh, no. This is the thiamine, right? So the thiamine has an extra methyl group, this guy here. Oh, I almost confused myself. And then now for the uracil is the one that has two carbonyl groups. Okay, so the difference between thiamine, okay, and uracil is that this thiamine will contain this extra methyl group. Okay, and then the uracil, you just see two carbonyl groups there, and there's no this methyl group. Okay, and then for the cytosine, it has to be carbonyl group and an amino group. Okay, so in case they ask you maybe about the purines, okay, so the difference between them is that in the guanine, okay, in the guanine you have the carbonyl group, and then in the adenine you have the amino group like that. So that's the difference. Okay, so in case it comes, you can screenshot this part and then try to memorize their structures. But what I've explained is basically these guys here. Okay, so the answer there, we're going to pick cytosine. Okay, and then let's continue. So we go to question 6. They're saying what pentose sugar has been modified in this drug? Okay, so what pentose sugar has been modified in this drug? So the pentose sugar there is simply deoxyribose. Okay, it's simply deoxyribose because the antiviral nucleoside analog, okay, they mimic what we call as deoxyribonucleosides. Okay, they mimic what we call deoxyribonucleases, meaning that they work like, okay, nucleosides, okay, which are some components of the DNA. So this sugar here that you can see here, this guy here, is just the deoxyribose. Okay, so this is cytosine and this is deoxyribose. Okay, so we move to question 7 now. Okay, so they're saying such type of drug would be incorporated into the viruses. Okay, so cytosine is found in DNA. So definitely the answer there is B. Okay, so if you had found that our nitrogenous base was uracil, okay, then that drug would be incorporated into the RNA. Okay, but the fact that it's we found that it was cytosine. Cytosine and thiamine are for DNA. And then this uracil is for RNA. So even if we had found that the nitrogenous base there was thiamine, here the answer will still be what? DNA. Okay. And if it was uracil, it will go to the RNA. Okay. And then number 8, they're saying the name of this drug is, and the drug of choice, uh, okay, they're saying the name of this drug is dash and is the drug of choice for treating dash. Okay, so that drug that is shown there, okay, is what we call as lamivudine. Okay, so lamivudine is used to treat hepatitis. Okay, it's used to treat hepatitis. Okay, so you go on your options, you check. So we see the option there on C. Okay, we see the options there on C. So why did I choose this drug? Okay, because lamivudine, okay, it's also called as 3TC. Okay, it's also called as 3TC. This 3TC is just a nucleoside analog. And that's what we were told in the introduction of the question. They said nucleoside analog. Okay, so it's a nucleoside analog used against, okay, hepatitis B to be specific. Okay, it is used against hepatitis B and sometimes even HIV. Okay, but the main disease that it treats, okay, it's hepatitis B. Okay, so you can master these others. Okay, maybe they can come in the exam. When they say HIV, okay, its drug is this guy here. Okay, and then herpes, its drug is this. And then this one here is just a nonsense option, this one here. So you can master that for HIV is zidovudine. Okay, and then for the herpes, it's I don't know how to pronounce this word, so you can read it. Okay, but that's for the herpes. And then for the viral hepatitis, especially hepatitis B, okay, you have lamivudine as the drug. Okay, so that is it on question 8. Okay, so now we'll move to question 9. Okay, so now let's look at question 9. So question 9, they're saying, what type of RNA is actually a biological catalyst? Okay, so here we have to know the work of um, these molecules that have been listed here to actually answer this question. Okay, so um, when you talk about mRNA, okay, we know that its function is to carry the genetic code. Okay, so the mRNA carries the genetic code. Okay, and then when you talk about tRNA, the T for transfer, this actually just transfers amino acids. Okay, it transfers amino acids. And then when you talk about the RNA, okay, so this is actually a structural part, okay, in what we call as ribosomes, okay, the RNA. The rRNA is actually a structural part in ribosomes. Okay, and then now ribozymes, this one here, ribozymes. These here are actually RNA molecules, okay, that have the enzymatic what activity. So the type of RNA that is actually a biological catalyst is what we call as ribozymes, like this. Yeah, what happens to my spelling? So ribozymes like this. Okay, this is the type of RNA that is actually a biological catalyst. So they act as enzymes. Okay, and then question 10, they're saying aspartame is dash. Okay, so this here is a very common question in your past papers. Okay, so aspartame is actually a sweetener. So it's 200 times sweeter than the normal sugar that you know. Okay, so aspartame is used, or I mean, aspartame is a sweetener. So it's used in artificial sweeteners. Okay, all right, so it's made from what we call as aspartic acid and phenylalanine methyl ester. That's where the aspartame comes from. Okay, so it's about 200 times better than the normal sugar. Okay, and then the antibiotic, the painkiller, the antioxidant, okay, these here are not related in any way to the aspartame. Okay, so the correct answer here is that aspartame is actually a sweetener. So we pick D as the best answer there. Okay, so now we'll move to the other part now, which is question 20, question 11 to 20, I mean. Okay, so question 11 to 20 will be based on this diagram here. So this diagram just shows some monosaccharides that we have. We have the D-ribose, we have the D-glucose, we have the D-fructose, we have the D-galactose, and the D-mannose. Okay, so that's what we've been given there. And then question 11, they're saying, what is the isomeric relationship between galactose and mannose? And then they've given us these options here. So for us to simply answer, okay, we have to know the meaning of these options that we've been given. Okay, so what are constitutional isomers? Okay, so constitutional isomers are just isomers made of the same things, but they differ in connectivity of the atoms. Okay, they differ in connectivity of the atoms. That's what constitutional isomers are. So when we look at galactose here, the D-galactose and the mannose, okay, they are made of the same thing quite all right, okay? But is the connectivity of these atoms different? No, okay? The connectivity there is not different. Why? Because this is carbon 1, there's O and H. Even there's O and H. Here, carbon 2, there's H and OH. Even here, there's OH and H. Okay, all the way up to down. It's just the same things, okay, that have been placed at different positions. Okay, so these ones, these two here, they can't be constitutional isomers because constitutional isomers define that the same structure, but the connectivity, okay, of the atoms is totally different. That's what constitutional isomers are. And then what are epimers? Okay, so epimers are actually isomers that differ at only one chiral carbon. Okay, so what is a chiral carbon? A chiral carbon is a carbon that is connected to 4 different items, okay, or 4 different groups. So now when I come here, okay, this guy here is a chiral carbon. Okay, this guy here is a chirocarbon. This guy here is a chirocarbon. Even this guy is a chirocarbon. This, and this are also chirocarbons. Okay, so epimers should only differ at one chirocarbon. But here we see that here at this chirocarbon, it's different between the mannose and the galactose. Here it's the same, quite all right. And then here it's also different. So these molecules here, the D-galactose and the D-mannose, differ at more than one. Okay, they differ at more than one chirocarbon. So they can't be epimers. Okay, they can't be epimers of each other. So the epimer is not the answer. Even the constitutional isomer is not the answer. Okay, and then in enantiomers, these are just mirror images of each other. So meaning that if I was to draw a line here, what I'm seeing here should be the exactly same thing that I'm seeing here. But it's not the case between these two structures there. Okay, here I have OH, but there I have H. So this one here is not acting as a mirror. So enantiomers will not be the answer. So the best answer here is these two here, the D-galactose and the D-mannose, are actually what we call as diastromers. Okay, they are diastromers of each other. So what are diastromers? Okay, diastromers are just simply stereoisomers that are not mirror images of each other. So we see that these guys here are not mirror images of each other because when I draw a mirror there, okay, what I see on either side is what is different. Okay, so they are diastromers. So you pick diastroma as the best answer there. And then 12, they're saying what type of structural representation are these monosaccharides shown in? So this is the Fisher projection. Okay, no need to even explain. When you just see vertical lines, horizontal lines, okay, describing the structure of a compound, that's the Fisher projection. And then this Haworth projection is when you represent these guys in form of a ring, like something like this. Okay, this is the Haworth projection. All right, and then this one here is the Fisher projection. So we just pick B there as the best answer. Okay, so we'll move on to question 13. Okay, so question 13, they're saying, what do the vertical and the horizontal bonds in each case represent? Okay, so remember when the structures that we are given, they were in this form here. Okay, we have these horizontal lines, and then we have this vertical line here. So the vertical line, okay, represents bonds that are projecting away from the viewer. Okay, they're projecting away from the viewer. And then the horizontal bonds represent bonds that are towards the viewer. So those bonds that are towards the viewer, okay, they are represented by what we call as a solid wedge. So something like this. This is a solid wedge. Okay, so solid wedge. And then we also have a dashed wedge that goes something like this. Okay, so this is a dashed wedge. So the solid wedge, okay, has the same meaning as the horizontal lines. So these horizontal lines here, okay, and the solid wedge mean the same thing. They represent bonds that are projecting towards the viewer. And then this dashed wedge and the vertical line, they represent the same thing. Okay, so they represent bonds that are projecting away from the viewer. So when I come here now on the options, they're saying uh, the vertical equals to solid wedges, while the horizontal equals to dashed wedges. Okay, so this is false because it's actually the opposite. So the vertical, okay, represents the dashed wedges, yes, and then the horizontal represents the solid wedge. Okay, so I'm going to pick B as my correct answer there. Okay, all right, and then question 14, what are they saying? Question 14, they're saying one of the monosaccharides above is known as the sweetest substance. Okay, what is the maximum number of stereoisomers that this monosaccharide can have based on the type of projection it has been drawn in? So when you go back to this structure here, okay, with the one that is showing these monosaccharides, which one here is considered as the sweetest? Okay, it's just fructose, we all know. Okay, it's just fructose. So I come here where the fructose is. And then the question is, how many okay? Or what is the maximum number of stereoisomers that this molecule can have? So the number of stereoisomers are equals to 2 to the power n. And then this n here represents the number of chirocenters or the chirocarbons that you have. So in this molecule here for the glucose, how many chirocenters do we have? So a chirocenter is just the carbon that is attached to 4 different groups. So we have this one here. It is attached to hydrogen, OH, this group above, and this group below. Okay, the other one is this guy. It is attached to H, OH, this group above, and this group below. The other one is here. It is attached to H, OH, this group below, and this whole group above. Okay, so there are 3 chirocenters in D-fructose. So I'm just going to say 2 to the power 3, which will just be what? 8. So the answer there is actually 8. So is 8 there? Yes. So we pick B there as the best answer. Okay, and then question 15, they're saying if the monosaccharide mentioned in the question above, meaning question 14, here I think they made an error. It's supposed to be question 14 above, was to cyclize, okay, or to form a ring. What type of ring does it form? Okay, and how many asymmetric carbons would it have? So when you draw something in Fisher projection, okay, and then now you cyclize it or you make it a ring, the number, okay, the number of chiral centers is going to increase by 1. So in this form here, we said it has 3, right? It has 3 chiral centers. Okay, so when it cyclizes, there's an additional chiral center that an additional chiral center that comes about. Okay, so this was in the assignment. So I solved that and I showed how this 4 comes about. Okay, so always when a sugar in the Fisher projection cyclizes, okay, there's a new chiral center that is formed. Okay, so in this form here, it has 3 chiral centers, but when it becomes a ring, okay, it has 4. So always there's an additional of 1 more chiral center. And then this guy here, when it cyclizes, okay, what type of ring does it form? So for the fructose, because it has a ketone group here, when it forms a ring, okay, it forms a ring that we call as furanose. Furanose. Okay, so furanose simply means a ring that has, it means a 5-membered ring. Okay, so always when fructose cyclizes, it forms a furanose ring. Okay, and then when galactose, mannose, and glucose, they cyclize, they form a 6-membered ring. Okay, so this 6-membered ring is what we call as pyranose. Okay, so in case they ask you for the others, just know that for the glucose, for the galactose, for the mannose, okay, it's pyranose. Why? Because they have an aldehyde here, okay, and they have 6 carbons in them. Okay, and then this guy here is also an aldehyde there, but it has 5 carbons. So meaning if D-ribose was to cyclize, it will also form a furanose ring. Okay, but for this glucose that has the ketone there, it's very much well known that it forms a furanose. So I'll just come here and say, let me look for an option that has furanose ring, okay, or furan ring, furan ring is just the same. And then the number of chiral centers has to increase by 1. So you see that option there, it is on what? Option D. So furan ring is the same as the furanose ring. Okay, so we pick D as the best answer. And then 16 is what I was explaining. They're saying which other monosaccharide on this list also forms the same type of ring as from the previous what? Question. Okay, so the other one there on those that have been listed is actually ribose. So ribose has 5 carbons, okay, in its structure, and it's an aldehyde. So if it has 5 carbons in its structure and then it's an aldehyde, it will form a furanose ring. Okay, and then these others here, they form the pyranose. Okay, so we pick A as the best answer. And then 17, they're saying which type of constitutional isomerism will not be possible between glucose and fructose. Okay, so let's look at their structures. So where's glucose, where's fructose? Okay, so glucose is here, fructose is here. So what type of isomerism can happen here? First of all, okay, a functional isomerism will happen here. The functional group isomerism will happen here. Why? Because in the fructose, I can see a ketone there. Okay, and then here I can see an aldehyde. Okay, this is just a carbonyl group at the beginning of uh, this structure. So it's called an aldehyde. And then if it's a carbonyl group, but not at the beginning of the structure, we call it as a ketone. So between these two, a functional group isomerism is possible. Okay, this fructose can turn into galactose. Can turn into glucose, and the glucose can turn into fructose by just shifting this functional group there. Okay, so the functional group isomerism is possible. Okay, and then constitutional isomerism is also possible here, because we remember what we defined constitutional isomerism was. Okay, we said the substance is made of the same atoms, okay, but they differ in their connectivity. So you see here, this oxygen is bonded to carbon 1, but here the oxygen is bonded to carbon 2. So that's difference, okay, in the connectivity. So constitutional isomerism will also work here, okay. And then when I go back to my options here, okay, so on my options, there's functional group isomerism. So this one is possible because of the functional group. The other one has the ketone, the other one has an aldehyde. Okay, and then the pyran furan isomerism is possible. Galactose, what do I keep saying galactose? The glucose can turn into a ring. So that is isomerism. The fructose can also turn into a ring. So the pyran furan isomerism is possible. Okay, and then the constitutional isomerism is also possible. And then now, what is this tautomerism? Okay, so tautomerism is not possible between galactose and fructose. So tautomerism involves what we call as a dynamic equilibrium and not a constitutional isomerism. Okay, so in tautomerism, there is the interconversion via the hydrogen shift. So the hydrogen atom, okay, maybe I should showing this track. The hydrogen atom maybe on here can shift and come there. Okay, the hydrogen atom can shift there and come here. So that cannot turn this glucose. That is not experienced in either glucose or fructose. Okay, so tautomerism is not experienced, okay, between fructose and galactose. So it will be the correct answer here. Okay, none of the above cannot be a correct answer, because this is true, this is true. So the only incorrect option, okay, for glucose and fructose is this tautomerism, because it means something else. Okay, and then question 18, they're saying by treatment of mannose, okay, with MBH4, what type of modified sugar is formed? So here the type of sugar that is formed is mannitol. Okay, so if I try to explain it, this NBH4 is what we call as sodium borohydrate. Okay, so sodium borohydrate is a reducing agent. Okay, so it reduces the carbonyl group of sugars to an alcohol sugar. Okay, so the resulting sugar for the mannose, okay, when its carbonyl group there is reduced to an alcohol, will just be mannitol. Okay, then mannosic acid, this one here, mannosidic acid, okay, that one is an oxidation product. Okay, but we said NBH reduces, so it can't be the answer. And then deoxy, mannitol, it's not a typical product. Okay, they're just putting it there to confuse you. And then mannozamine is an amino sugar. Okay, but we are looking for a sugar alcohol, which is just what? Mannitol. So here the correct answer is mannitol. And then what is the meaning of a solid wedge? Okay, I already explained this. A solid wedge simply means bonds that are coming towards you. Okay, they are coming out of the plane towards you. That's what the solid wedge means. Okay, so here I'm going to choose option A. So a bond projecting towards the viewer. That's what the solid wedge means. And then the dashed wedge, it means a bond projecting away from the viewer. Okay, let's look at question number 20. So on question number 20, they're saying the two modified monosaccharides found in peptoglycan are N-acetylmuramic acid and dash. Okay, so this question here is direct from the notes. Okay, this question here is direct from the notes. So this peptoglycan, okay, is made up of N-acetylmuramic acid, okay, and N-acetylglucosamine. Okay, so you choose A there as the best answer. Okay, so thank you so much for watching this video. Okay, if you'd like to access the full video solutions, okay, to this paper, as well as other papers, okay, including exam papers, including tutorial sheets, okay, you're welcome to register with us on our website. You're going to find all the answers to these questions here. Okay. Okay, so those who'd like to register with us, you can check out the link in the description below. Okay, you're going to find the link that has the registration video guide on how you can register with us and be able to access the past papers and the tutorial sheet solutions, as well as the topic lessons. Okay, so when you come on our website, you see something like this. So you register for this course here, chemistry. Okay, and then you open the course. Okay, and then you go in bio and organic chemistry if you are second semester at Apex. Okay, if you're at any other university or first semester at Apex, you go in general chemistry. So if you go to the bio and organic folder there, you're going to find lessons and tutorials on each topic. You're going to find summarized notes, okay, and then you're going to find the tutorial sheets here. So you can go there, all the tutorial sheets, we have the solutions, and then the past papers, you're going to find them in this folder here. Okay, so thank you so much and all the best as you prepare for the exam.